let's go ahead and take a look at lesson 2.5, the precise definition of a limit. This section is probably the most abstract section we'll encounter in this course, so it may appear difficult. It looks complex. It could be confusing, the language, but it is at the heart of the definition. Well, not the heart, it is the definition of a limit, but it's kind of the heart of what mathematicians do. So those of you who are going to be math majors, this is a kind of discussions and things you do once you get beyond calculus, all your calculus courses, and get into the upper division mathematics. You start talking about ideas like this here. So this is just a small taste of that. So we introduce a definition for the limit of a function. We've seen it through tables, we've seen it through graphs, but that is just more of an inductive kind of reasoning to show what the limit is and see it. We need some formal definition to help us, right, to really, right, focus on and define what a limit is. And so this is what produces this more complex arrangement of symbols and mathematical expressions, right? And so the first thing I want to clean up is in this epsilon delta definition of the limit is this notation here. So this is very important to kind of read because we see these absolute values, and the absolute value is what we use to measure distance or how close two values are to each other. And so you can see when we see statements like this, you see the distance between f of x and L is less than epsilon, meaning that the value of the function and the limit get really close to each other, right? So close that it's smaller than the closeness of them is less than epsilon. That's the epsilon symbol. And here you're saying the delta, the distance between x and the value you're approaching, right, is x minus a, the difference between them, the closeness of them, right, is less than delta and greater than 0, meaning that, again, because absolute value is greater than 0, is a positive value. So we have this statement here. We're getting closer and closer to the x value, okay? Let's take a look at, again, the equivalent statements. So if you don't like absolute value, you can also think about these statements meaning this over here. And you think, well, how does that become that? Well, when we rewrite an absolute value, right, you put a negative to both sides, and then you add a to both sides. So that's where you'll get the delta plus a, and then you'll get the a minus delta. As we think about what this would be when you solve an absolute value, how you rearrange the inequalities, it becomes this. We're really, again, looking at how close is the value a coming to x. Now, when we look at this definition here, the limit of f of x equals L as x approaches a, if, right, only, and again, this may not make sense, for every epsilon, there exists a delta greater than 0 such that the distance between the value we're approaching in x is less than that delta. And, right, if that's true, then f of x minus L, the distance between the function and the limit, is less than epsilon. Now, again, this is so that we can show that the limit exists for any of these values. And so these pictures here do try to represent what's happening here. Now, using this here, I like to use that media to kind of show. So, for example, here's the function square root of x minus 1. And what we're saying, what's the limit of this function as x approaches 5? What's the limit? Well, it's continuous. I can plug it in there. 5 minus 1 is 4. Square root of 4 is 2. So we know the limit's 2. Now, the game we're playing, it says the limit is 2 only if for any epsilon, here's the epsilon. Epsilon is the distance away from the function at 2. So you can see as I'm getting, look at the yellow part, it's getting bigger as my epsilon's getting bigger. So I'm getting further away. The epsilon's getting smaller as the epsilon gets smaller, I get closer and closer to the function. So no matter any epsilon, someone's playing a game and says, okay, I'm going to make an epsilon of 1. Okay, let's make it 1. Then someone says, you should be able to find, there's what I'm talking about there, a delta, some value that's close. And so here you can see as I get closer and closer to as I approach 5, right, my values of my function are within epsilon, like the limit's 2. So if epsilon's 1, my limits are, my boundaries are 1 and 3. And so I can find a delta, right? There's a delta right there, a delta of 3. So if I'm within 3 units of 5, I'm within 1 unit of the function or the limit. And so no matter what epsilon I give you, no matter how small, I can find a delta, I can find a delta where my function is always in between those borders. And that's the game we're playing. Someone says, oh, 0.4, okay, let's go down to 0.1. No, let's get past it. 0.3, 0.2. Can I find a delta? See, now, if my delta is too big, my values of my function are here and here. It's way beyond the boundaries. But if I get closer and closer to 5, at some point, I come within the yellow marks, and see it's all green there. And so that's the game we're playing, right, with this delta epsilon. And so you're with the delta epsilon delta definition. So I had, this is a link to my notes that I put in the to my hints, right, for the homework. There's the definition explaining, and again, looking at some of the notation here. What happens if I do the infinite one here? There's some notation here. So when demonstrating the limit of this equals 2, which we know because you plug -1, with epsilon equals 0.3, what of the following delta values suffices? Meaning, how close do I need to get to -1, right? So that my function is within 0.3 of the limit 2. And so we're trying to play that game there. You use the definition that we have, right? I'm missing a less than symbol right there. But if given epsilon equals 0.3, we need to find a delta greater than 0 such that if the distance between x minus a is less than delta, then the distance between f of x and the limit is less than epsilon. So we're trying to now find what that delta is. If we're saying epsilon 0.3, then how close do I need to be, right, to -1 as I approach x, as x approaches -1. That's what I'm trying to find there. Again, there should be a less than symbol there. And so then you get into this algebra here, right? F of x minus 2, the limit has to be less than 0.3. And then you rewrite this. And as you rewrite that, you'll see magically, and this is kind of awesome with the proof, is that you end up with this absolute value x plus 1, which matches up to this part of the definition, x minus a. A is -1, so there's your x plus 1 is less than delta. So because of that, we end up magically, when we solve for that, we have the absolute value of x plus 1 is less than 0.15. And that matches up nicely. We know the absolute value x plus 1, we know that is less than delta. And so we can then say delta has to be less than or equal to 0.15. If that's the case, then I will always be less than 0.3 of epsilon, meaning if I'm that close to -1, I'm only 0.15 away from -1, then I can always show that my function falls within the limit. I'm getting closer and closer to the limit of 2. And so that's what we're kind of doing here again. Sorry about that. That's what we're trying to show. Let me escape out of that. And then again, you could use some of these or some of my notes trying to explain. This one is talking about infinity, right? Getting really close to the, as I approach a value, right? Any number, like given 1,000, how close can I get so that my function is greater than 1,000? So anytime anyone gives me some value, I should be able to find a value. I should be able to get as close as possible and then be greater than any number. Here's 1,000, but I can be greater than any number. And so you can see some mathematics for this sample problem that I have here. What was one more? I did that one. Continue on. And then I think one of the problems on the homework set, you're asked to use Desmos, and I made a note of sometimes it doesn't work and you're trying to find, again, you're trying to determine the delta given some epsilon. And so given that case, again, you can see the mathematics that I'm doing using the definition, right? As x approaches some value, right? It should be less than delta, meaning I'm getting closer and closer. Here, then my function is getting closer and closer to the limit. How close? 0.001. Remember, the limit was equal to 1. As x approaches 1, our limit is 1 also in this case. So again, you would use the mathematics to find which value of delta. Now, there's one problem somewhere where you have to decide between the minimum value. I wonder if it's here. Oh, in the notes here, because the functions are not, notice, like when you look at these functions, they're not equally distant from a, from here to here. So when we're talking about delta, delta is this distance away from here to here. But when we're solving for them, you end up with following this problem solving strategy, which is a good way to kind of march your way through these proofs, and you can fill in the blanks here so that it pretty much marches down this way. So for the time being, you may just kind of memorize that. But there is a part where we need to kind of decide between the minimum value. The answer is the minimum value between these two. I'm looking for that example. Where was it? As we do that, you have to decide between the minimum, like the delta is not equal on both sides. And so the delta we will use is always the minimum of your two options, right? And that goes back to, let me just show you the picture again. As we're trying to find a delta right here, the delta we would state is the one that's closest to the value we're approaching. So whenever you end up with two different potential delta values, we use the minimum of that one, because that one ensures that we will always be within that range. If I use the bigger one, then that bigger one is beyond, right? We want to use the smaller one so it encompasses both of them. But I think that's it for now. So there's our quick review for 2.5.